We'll take a look at the review sheet. Number one, the two stores selling watermelons. So the first store, so I'll just call it store A, sells watermelons, average 2 pounds, standard deviation of 2.5 pounds. And store B sells watermelons that average slightly less, but a little bit more consistent at 2 pounds. So we're going to select a random one at each store. What's the mean and standard deviation of the difference in weights? So for part A, we're just going to basically say what's the expected value of A minus B? Well, that's just 2 minus 1.8, so we would expect about a 0.2 pound difference in weights. The standard deviation of A minus B, remember that we first have to go to variance, 2.5 squared and 2 squared, and you always add the variances. And so that will be 3.2 pounds for the standard deviation of the difference between the two. So if a normal model can be used, what's the probability the melon you get at the first store is heavier? So in other words, what's the probability that A is bigger than B? Well, we don't have a critical value, so we'll play our quick trick here that A minus B is greater than 0, right? Subtract B from both sides. Well, from here, we know that this is A minus B. We know it's normally distributed, and we just saw the mean was 0.2, and the standard deviation was 3.2. So our z-score here, critical value is 0, minus a mean of 0.2 over a standard deviation of 3.2, and that is negative 0.0625. And if we were to put that on our curve just to keep getting that good practice, this curve is centered at 0.2, and so 0 is about right here, and we want everything above that. So we should be looking at something just over 50%. Since this is a normal curve, we can use normal CDF. And so the lower bound is 0, the upper bound is infinity, mean of 0.2, standard deviation of 3.2. And so the probability that A was bigger than B should be about 0.525. So on to part C. So for part C, it asks the first store sells them at 32 cents. 32 cents. Store B sells their watermelons for 25 cents. So find the mean and standard deviation of the difference in prices. Well, what we're going to have to do first is make a quick conversion. So we're going to take A and multiply by 0.32. And so that's going to end up being 64 cents a pound, 0.8 here. And we're going to take B, and since we're converting from pounds to money, we're just going to multiply both of these through. And so now, just go ahead, just like we did before, find the mean and standard deviation and the difference of those two prices. So in other words, what's the expected value now of 32A minus 0.25B? And what's the standard deviation of 0.32A minus 25 cents times B? So that'd be 0.64 minus 0.45 up here, which is a difference of about 19 cents a pound. And again, remember, we're always going to go to variance, 0.8 squared, and you're always going to add 0.5 squared, and that's about 94 cents on that standard deviation. So we go to number 2, our Olympic archer. Assuming each shot is independent of the 6 arrows, what are the following results? So this is a mix and match of binomial and geometric. So here's what I'm going to do real quick. Let's run through to make sure we recognize which situation is which. So we can see, excuse me, first bullseye on the third arrow, A is geometric. Misses a bullseye at least once. That's geometric. binomial, excuse me. Her first bullseye comes on the fourth or fifth arrow, so C is geometric. Now it looks like D, E, and F. Like D, E, and F are all binomial. So let's go through real quick. You got two outcomes. Right? That's hit or miss. It's the same over here for geometric. Get hit or miss. Each shot is independent. We were given that information. Right? Same thing over here. Each shot independent. 3, we know the probability that we hit is 0.80, and that's not changing. So here they are right next to each other. You can see the first three conditions, at least the way I've set them up, are exactly the same. However, when we get down here to number 4, with all these binomials, we're taking 6 shots. With A and C, we're going until success. So you can see right next to each other how those things are going to play out. So for A, I'm going to do A and C right here. So we're going to define X equals number of shots until success. So I'll do A and C together since they're both binomial or geometric. So for A, probability her first bullseye comes on the third arrow, X equals 3. Really, you could go to geometric PDF here if you wanted to. I think it's almost just as easy. That'd be a miss, followed by a hit, which is 0.032. For part C, again, I'm just doing this one because it's the other geometric. Here we're going to go probability that X equals 4 or X equals 5. A little bit different because it's not, at least 5 shots to make, at least 5 shots to make the bullseye. So we're not going all the way from 5 down. So what we could do here is we could do geometric PDF. And remember, if you take a look at that, the first thing you want is your probability, which is 0.8, well, 4. And then geometric PDF again, 0.8 as well, but this time we're going with 5 shots. And that is 0.00768. Not very likely that it takes that long for a very good archer to hit the bullseye. It'd be a bad day for him. So we'll take a look at B, D, E, and F now. B, she misses the bullseye at least once. Well, remember, we're doing everything here in terms of hits. So X will be number of hits out of 6. So that'll be the case for B, D, E, and F. So here, at least, right, misses at least once. So that just means she can't hit all 6 times. So really, that's the probability that X is less than or equal to 5. Here, that's set up very nicely. That's a CDF. So out of the 6 shots at 0.8, 5, and for us, that's 0.738. For D, first, she gets exactly 4 bullseyes, so probability that X equals 4, and that's binomial PDF. That's the way that we're going to set it up. If you'd like to do the table, by all means, go for it. And for us here, that's going to be 0.246. Right. For E, she gets at least. Probability that X is at least 4 bullseyes. Now to use a calculator, remember we're going to do 1 minus the opposite of at least 4, which is less than or equal to 3. And if you use your 1 minus binomial CDF, that should be 0.901. And then finally for F, no more than 4 bullseyes. That's just, again, binomial CDF. And that probability is going to be 0.345. All right, we'll take a look at number 3, the swimmers. So we have all that information in the table. We're told that things are independent, which is good. Basically, the checklist is gone. They kind of done the checklist for us up at the top. So what we're going to do, mean and standard deviation for the total time. So the expected total. So that's going to be, right, swimmer 1 plus swimmer 2 plus swimmer 3 plus swimmer 4. So for us, that's 50.72 plus 55.51 plus 49.43 plus 44.91. And so that expected total time is 200.57 seconds. Standard deviation for the total. Again, we're combining different variables. We have to combine variances. 0.24 squared, 0.22 squared, plus 0.25 squared, plus 0.21 squared. And then to get back to standard deviation, take the square root of all of that. And so the variance, or the standard deviation, excuse me, for us would be 0.461 seconds. And again, you can see that's more variation than any of the individual swimmers, which we would expect when we put more stuff together. So there's part A, the expected mean and standard deviation. And I have a feeling with part B, the team's best time so far was 3:19, so 199.48 seconds. Are they likely to swim faster than this at the conference championship? All they're really asking us to do is let's find the probability that X is under 199.48 seconds. So their best time's a little bit faster than we would expect. So basically, let's just do a normal distribution, right? If you look back at the stipulations, they're normally distributed. So X is going to be team's total time. We want to get into this habit of defining our variable. So if we know it's normal, let's go ahead and get a quick z-score. The critical value for us is 199.48. We just saw above, we've got a mean, we've got an expected value. We've also got a standard deviation already. And so if we do all that, we are basically 2.36 standard deviations below. That's starting to get a little bit out there, right? That's a good chunk away, right? Just to keep ourselves in this habit, right? This one's going to be centered, right? We would expect the score, the times to be somewhere around 200.57. We're 2.36 standard deviations away, so somewhere down in here, here's that 199.48, their best time for the season. So we can run a quick normal CDF to figure out the exact probability. Already, I might be a little skeptical. We're over 2 standard deviations away, but let's run a probability and just see. So normal CDF, so we're going from negative infinity up to 199.48 with a mean of 200.57 and a standard deviation of 0.461. So the probability that this team swims under 199.48 seconds is 0.009. So there's about a 1% chance that they swim better under personal best, which isn't very likely. So about once out of every 100 swims they would do it. So, so we'll use our knowledge of normal distribution to answer that question.